Hi, everyone. Welcome back to this last live Q&A session for System and Skill 2022. My name is Yun Jin. I'm an engineering director at Meta. I will be host for this conversation. First, I want to thanks for all the presenters for their great talk. In today's panel, we have David Meisner from Meta, Rosemary Wang from HashiCorp. We have Kenny Yu and Ranjith Kumar from Meta as well. So before we get into conversation, first I just want to check where everyone is, because in pandemic, everyone can be anywhere, right? So I want to start with myself. Usually I'm staying in Bay Area. Actually, I haven't been leaving Bay Area for more than 2 years now. But today I'm in New York. This is my second trip in 3 years. David, where are you?
I am in my apartment in San Francisco today.
Oh, cool. Rosemary, where are you?
I'm right across the water from you in New Jersey. I'll wave to you in the window, but
okay.
we're separated by a river today.
Okay, cool. Kenny, I saw your background is a Golden Gate Bridge. Is that where you are?
Yes, this is pretty accurate, except I'm on the wrong side of the bridge. I'm also in San Francisco.
Oh, cool. Ranjith, where are you?
I'm in San Francisco, but I'm currently visiting Bellevue, Seattle.
Oh, you're in Washington State. Nice. Okay, cool. That's a benefit of a virtual event. We can easily, put everyone together. Cool. So now let's go to the questions. So we are having questions coming from live, or there are questions previously sent to us from the blogs. The first question is to Rosemary. Why does Terraform take a declarative approach to provisioning and configuring infrastructure?
Yeah, it's a great question. I think it's good to back up and explain what's the alternative to declarative, and that's imperative, right? So there's two paradigms. There's the imperative paradigm and the declarative paradigm. Imperative is where you can express how you want your control flow to work. So you explain step by step, this is how I expect to change something. It could be code, it could be infrastructure. The declarative paradigm is deciding what you want, right? So you want the target state, and the tool itself or software that you have determines that target state. The reason why Terraform in general started or really focused on a declarative approach was that most people don't want to sit and decide the control flow of how they configure their infrastructure. There's an unpredictability to that, and that leads to failed changes. So if you offer some software or a layer of abstraction that handles the imperative control flow of configuring your infrastructure for you, and all you need to do as an end user is declare the state that you want or the desired configuration, it lends to predictability in the sequence of changes, as well as the kinds of ways that you handle rollback, et cetera. So part of the reason why Terraform did this is to make it predictable, and also so that it's easier for us to continue to extend. We have a lot of plugins and many different target APIs. It's really great when someone's able to handle and understand the behaviors of different APIs in the plugin itself, and not necessarily have to think about from an end user standpoint, I need to do X, Y, and Z in order to configure a target infrastructure resource.
Cool, thank you very much. This is a great answer. So David, you talked about ICSP in today's talk, which is an internal, private cloud management solution. So I'm curious, most people are probably not familiar with it. How do you compare ICSP with things like Terraform or CloudFormation or Kubernetes operator? Could you elaborate a little bit more?
Yeah, it's a great question. So I think at the high level, again, ICSP is a all-in platform where you can declare how you want your service to be operated and access different capabilities like routing, deployment, so on and so forth. As you go and look at the layers within ICSP that I mentioned today, I think you'll see a bunch of similarities in some of the design aspirations. So like declarative configuration is like one dimension that Rosemary just touched on. And I think we have very similar opinions about the benefits of declarative. in that asking the user like what they want to have is advantageous versus them basically specifying every single step to the platform, which can be kind of rigid. Raising the level of abstraction and capturing their intent allows the platform to take on a lot of the work for them, ideally. And so similarly, like with Kubernetes operators, I think you'll see in some of our layers similar kind of conceptualization of things we need to do, like resources, like what are the resources that the service owns, and the fact that there's controllers making sure that those resources are in the states that we want them to be. And so there are definitely like similarities between these systems, especially in how we encapsulate some of these responsibilities into these concepts. I think the main differences with ICSP are as we think about the like domain API that we mentioned in the talk, that is the interface to these different capabilities. We're pushing for a very high level of uniform behavior and expectation of what these APIs can do. So things like understanding a topology of a service across all the APIs, they're all expected to kind of conform to this behavior in their signature. Or understanding of things like multi-tenancy is I think something that we're pushing on very strongly in ICSP in compared to the other systems, which are very flexible, but it's very hard to kind of ensure that everyone like using and implementing some of these like resource providers, for example, are going to have exactly the same behavior in their API. And that largely comes from the fact that we are like more of a private cloud setup, and we are both the provider and consumer, and we can do this. I think the challenge for these other systems is very real, that they have to support a large variety of use cases, and that's very challenging. So I think we're optimizing for slightly different setups, and you'll see that in the some of these areas.
Cool, thank you very much. So next we got several questions about Kenny and Ranjith's topic. So Kenny and Ranjith, you guys talked about the global capacity management in Meta as a private cloud. So this is a very interesting topic because it's not a common paradigm we see in public cloud. So in your view, what are the key benefits for this approach?
Yeah, I can share my view. So I think there's a clouds have to find the right balance between taking the complexity taken on by the cloud provider and the complexity taken on by the service owners. And in public clouds, typically the public cloud provider doesn't have as much understanding of the workloads that are running in public clouds, whereas in private clouds like Meta, we do. So this gives us the ability to take on more of the complexity away from service owners and provide a higher level of abstraction and automation to change things. So overall, the benefits of this approach that we've seen at Meta so far is that this really helps abstract service owners away from the physical details of how regions or zones work, zones using the public terminology. So for example, service owners don't need to worry about hardware refresh, hardware decommissioning, new region turnups. From the service owner's point of view, it's what they observe is that their capacity is rebalancing across the regions automatically. And the benefit for infra is that infra has more flexibility to change the placement to optimize for different goals. For example, if we do want to do a hardware refresh, we can shift the services away from the regions where we need to reclaim the resources. And this can be done transparently as long as all the constraints are satisfied.
Cool, thank you. This is a great explanation. I think a follow-up question here is, what are the key enablers for Meta to do global capacity management?
Yeah. Reggie, you want to take that one?
Yeah, so thinking of as follow-up to the previous question, like we both need the ability to understand and model the various workloads we have, and also have a very clear understanding of the contract with these various services, and not only to the services, but also to the REs, which allow us to come up with concrete plans to know what our fluidity is, to go from one region to another, or from one zone to another, to actually know what our capability and what can we move, and to come up with plans that's both constructive and also like optimal globally.
Cool, thanks. A live question just coming in regarding to this topic. How do you determine the regions to place the services if service owner just reserve the space globally?
Yeah, at least for global reservations, the services are typically latency tolerant. So they could, in practice, run in any region as long as certain guarantees are satisfied. And those guarantees are, if they requested, let's say 100 machines, they should always have at least 100 machines. And also, if one region is unavailable in our fleet, they should still have at least 100 machines available. So that's the fault tolerance guarantee we provide. So given those constraints, we feed the constraints into our solver. And then one of the goals of the solver is generally to minimize the number of machines used. So, and what this means in practice, if every region supply is equal, their global reservation will probably spread equally amongst all the regions with a few extra machines as fault tolerance. But this may not be the case. For example, if our regional supply is imbalanced, they might have more presence in the one region and less presence in another region, but those same guarantees will still hold.
Thank you. So next question back to David. How are the dependency between controllers are managed?
Yeah, so there's many different pieces of state or other forms of information that different controllers may need to communicate. So as an example, our deployment system and our routing system need to communicate at least through the form, like through discovery, in order to figure out, hey, like where are the new deployments and how do I route to them? One thing to highlight about ICSP's design is that at the API level, we make sure that the inputs and outputs between each of these systems is made explicit. And these inputs and outputs are kind of declared into the control plane so that these systems can negotiate with each other. And this is an important difference than other systems in the sense that there's no intermediation of these dependencies by ICSP. So concretely what this means is, for example, we can set up front where a location in the control plane that the domains of deployment and routing will find the information for discovery. However, once that location is established in the control plane, now the deployment and routing controllers can interact directly, and there's no kind of third-party system changing the state for these systems. So it's an important contrast to other systems you might expect, where there's maybe some kind of super level system that as state is changing, it is manually updating one controller to another. This is all delegated down to the controller interactions once it's initially, these dependencies are initially set up in the control plane and in terms of addresses.
Cool, thank you. So next we have a set of questions about Terraform's, I guess, consistency management. So Rosemary, what is state? Why is state and the state locking so important in Terraform? And does Terraform support transactions? What happens when we apply heat, when we apply heat an arrow in the middle of a set of changes?
Yeah, so there's a lot to unpack. And meanwhile, the sirens are going on outside. So apologize if there's some noise that's crossing in. So I'll repeat anything that needs to be repeated. But we'll start with state in general, right? Terraform, similar to the control plane David was talking about before, it's the idea that there has to be one reflection of state of the infrastructure, right? Whether it be dependencies as well as configuration. So Terraform itself has a schema that it represents a state. And the schema includes I would say even the individual states of the resources that are under configuration. Now, when you run Terraform and you run an apply, what that does is that locks the state, and that prevents other transactions from happening. So what this is doing is preserving the predictability of the changes that you're hoping to apply, right? So it's sequencing the changes so that you are not creating conflicting changes upon individual resources. So that's why state and state locking is very important in the case of Terraform. It's to force sequential, or in some ways a more predictable way of applying those changes in order. The second question was, does Terraform support transactions? You can consider it a transaction per resource. So in Terraform, you can declare a resource, right, as part of the domain-specific language or programming language if you use CDK for Terraform. But the idea is that you have a transaction per resource. And that was the dependency graph that I was showing earlier. The idea is that anything that you change from an individual resource level undergoes a single transaction. So when an apply it hits an error in the middle of the set of changes, it will stop at that resource. Now, if there are other resources that don't depend on it, right, from a graph perspective, if there are no dependencies, then it will continue to proceed and configure up to the resources that, up to the resources that don't depend on it, right? But once it hits an error with the resource, a specific resource, it could be, let's say, a network for some reason, then it will stop and it will reflect that individual resources state in the overall Terraform state schema. So what this will do is mark this as failed or mark this as something that needs to be reapplied. So the next time you go back and reapply and you've either rolled forward new changes or resolved some of those errors, either manually or within your own infrastructure's code configuration, Terraform will resume configuring that resource. So we'll do, once again, a refresh of all the resources related to that configuration and then resume that single resource transaction effectively. It's not really a roll back necessarily. You do have to have some manual configuration in order to resolve that error. But once you reapply, Terraform will return to the individual resource that has failed.
Cool, thank you very much. Okay, so next question is for Kenny and Ranjith. For regional fluidity, you mentioned using distributed tracing to understand the service dependencies and the demand distribution. How accurate is this demand distribution attribution? What are the limitations for this approach?
Yeah, when we think of understanding tracing, I think there is a significant amount of effort that's needed for us to first cover tracing better overall for all the loads and all the traffics that we have. And once we have, so there is an accuracy notion there itself. And after that, these entities or these demand sources are concepts that we defined to show us the ability to shift them, right? So based on our definition, we would need to like explicitly attribute a certain format for those specific REs that we are trying to cover. And this would also has an additional cost on top of it. And this would mean there is a certain coverage loss when it comes to tracing. And on top of that, to cover a specific demand source completely, there is an additional possibility of a certain loss because we might not cover all the sources that's adding into that. And on top of this, there are also additional complications that can sneak in from our routing logics and routing policies that add on top of to that demand source. For instance, do we route globally or do we route regionally? And how does this impact based on calls that impact databases and so on. So those are some of the limitations or additional complexities that makes it a little bit harder. And especially if you want to cover the entire private cloud or public cloud's traffic, it would require us to sort of invest a little bit more there since these are not like automatic definitions that we can derive today.
I just want to add on to that. I think distributed tracing is great for request response types of workloads, which is a significant portion of our traffic. But a lot of our services internally are not necessarily request response based. Example is AI training workloads. There are no requests or responses. It's just understanding the training data. And so we have other types of these types of workloads, which distributed tracing is not a great fit for understanding their service dependencies.
Cool, thank you. Our next question is for Rosemary, but I wonder whether this question applies to SSP as well. So let's start with Rosemary. Can Terraform be run automatically in response to some event or change in the infrastructure?
Yes, but you do have to build it or use a separate tool to do that. So if you're downloading open source Terraform binary, it's not going to have some kind of event response, right? You will have to add something on top of it. You can do a couple different ways. Some folks use console Terraform sync, which responds, basically it runs a Terraform module in response to changes to HashiCorp console service catalog. Some people use a Kubernetes operator in which they run a Terraform module in Kubernetes and then configure something, configure a target API somewhere. There's also, the ability to do drift detection in various tools as well. So drift detection is an event. So if there is an event, there's a difference between what your infrastructure as code is saying as well as the actual state of the resource. Drift detection is a popular question I get. And there's the ability to do auto remediation, but just not within the Terraform open source tool. You will have to add either a tool or your own layer of abstraction on top of that.
Cool. David, I wonder, do you think this question applies to SSP? Do you have any thoughts to add here?
Yeah, I think so. So first of all, at least in terms of how I interpret events, there's a bunch of different types of events we might want to handle in the infrastructure, from maybe like a DR event to some other platform that wants to interact with ICSP. So depending on the kind of event, we'll probably handle this in different ways. So for example, some forms of events in our infrastructure are actually handled in the layers below us, like our deployment system kind of inherently abstracts this into what it encapsulates. However, there are definitely forms of these events, like some platform wants to make an automated update to ICSP or other kind of updates from one system to another. So I think that in those categories, the main thing I wanted to point out with ICSP is we definitely are able to take information through what we call the automation pathway. And what this really means that I wanted to highlight is that we do a fairly intentional separation of configuration coming from users and configuration coming from automation systems. So this could be those events. And we store them in separate locations so that we can have policies about how the controllers want to act on things coming from humans and automation pathways like events, or even kind of site event scenarios that need to have the final say in how we want the system to act. So I think the main thing to point out is that the system absolutely can act on these events. But we try and create a clean separation between the human authoring and storage locations and the automation authoring and storage locations, so that we don't accidentally get into automation and humans having conflicting instructions to the system.
Cool, thank you. Yeah, this next is a really interesting question. I think probably very important for a lot of people who are considering using cloud. So Rosemary, when scaling infrastructure, especially with the public clouds, cost becomes a major concern. Can you explain more about techniques to mitigate cost and increase resource efficiency in testing and the production environments?
Yeah, it was actually really fortuitous. But Kenny Ranjith's talk was actually a place because a lot of the same techniques apply in understanding what kind of capacity you need, but also what kind of workloads you're running as well. A lot of the times when you start out with public cloud, it's easy just to run workloads, whatever you want, because you can self-service it and you get it. And for the most part, you get the bill and that's it. But it's important to put a few techniques in place and just to mitigate it over time. Once you get an understanding and you get visibility into what kind of workloads you are running, the services you're using from a public cloud standpoint, there are techniques that you can add, including requiring the auto scaling of resources. Auto scaling's fairly a popular way to take advantage of the elasticity that you need at any given point in time based on demand. There's also ways that you can add additional visibility and control over tagging. In public clouds, I highly recommend using some sort of kind of expiration tagging for testing environments. That way you're limiting the amount of time that these resources are up. Now, if they are continuously being updated and changed, then the expiration tag just continues to renew. But if they're not being changed, this gives you the ability to automatically remove those resources and clean them up. There's a lot of hygiene in general regarding infrastructure resources. So making sure you have the visibility to audit the resources that are being created and used. And on top of that, there's a lot of interesting techniques now using no testing environments, just basically creating production environments and duplicating them, treating them all as individual sort of representations of new changes to their whole infrastructure systems, and then just switching it over. So it's not even testing or production environments. It's just blue-green, you're constantly doing a blue-green. So you're doing one production, next production, next production. So some folks have started to think about that as a way to mitigate some of the cost. So it's doing this on demand and not just keeping a persistent environment around. But those are some of the more common ways to do it. There are more unique ways that you can do this depending on the type of demand you run, as well as the type of environment and public cloud that you're running on.
Cool. Thanks for all the tips. So next question is to Kenny and Ranjith about some implementations details for global capacity management. So how quickly can global reservation and the regional fluidity shift services across regions? How frequently is this done?
Yep, I can start with global reservations. So the services running in global reservations are latency tolerant. And so we can shift them pretty frequently. The limiting factor is how quickly the Twine containers that are running those jobs can stop and restart. So collectively for all the Twine jobs running in global reservations, we can probably shift them in about 1 to 3 hours. And we can do this, we do this shift with the solvers running continuously, and we can do this shift anytime. But typically, once we've converged on the stable solution, there are no shifts that will happen after that. Ranjith?
For regional fluidity, the time is going to depend on which demand source we are shifting and how big the demand source spread is and how many services we are impacting. The lot of contribution factors to slowness or the viscosity comes from the ability for the services to actually move and be able to move in an automated fashion as well. So today this is in the order of weeks, and this is being consistently improved based on the automation which we invest in on various parts of this.
Oh, thank you. Next question, I think this in similar realm. How also for Kenny and Ranjith, how long do solvers for global reservations and regional fluidity take to run? How extensible are those solvers to incorporate a new type of constraints or goals?
So I can start with global reservations. The solver is using a mixed integer linear programming problem underneath, which is an NP complete problem. And so the way the solver is implemented is the more time we give it, the more optimal solution it can find. But we can always stop at any time and it will take the best solution it's found so far. And everything we do is we use the previous solution as the starting assignment for the next solver. So over time, it will converge to the best solution. So in the worst case, we put a hard cap at 20 minutes. But what we've observed so far is that once we've converged at the optimal solution, it can run in 5 minutes. And then for the extensibility question, it's fairly easy to add a new constraint or goal using the solver library we have internally at Meta. For example, we were able to add a goal to minimize machines used with maybe less than 100 lines of code that saved a significant number of machines recently. And that was added very easily. Ranjith?
Yeah, so there are a mixture of solvers mainly to understand from a linear estimation level how much capacity that we would want to provide to various entities. And then an additional extension to figure out how we can leverage the service modeling into the solver so that we come up with more accurate estimations based on the actual service model. With respect to solving time, it is based on the intent and again the spread of how big our intents are and how much we are trying to shift. So this can go somewhere from half an hour to a couple of hours based on the intent. With respect to extensibility, there are various cases or various additions that we can add on top of the existing constraints. And there is a cleaner framework to both provide these constraints, whether it's related to minimum presence or explicitly like reducing the overall disaster recovery cost, etc. And that's also taken into account based on the runs we do.
Cool, thank you much. Yeah, we have time for one last question. Rosemary, you mentioned the importance of modularizing infrastructure components. How do you make sure you can change one module without affecting its dependencies?
Yeah, so there are a few ways to do it. Part of this is expressing the dependencies not within, let's say, your infrastructure as code tool like Terraform. I shared one technique, but another technique that I think I heard ICSP is using involves surfacing the config, sort of that config out right from the declaration itself and into sort of a different place, right? So you can use it in a configuration manager, et cetera. It's pretty successful being able to surface this into a configuration manager, having your module retrieve it. The other way, and that was also something that ICSP does, is contract testing, right? How do you know the inputs and outputs are truly the actual parameters that you need when you're connecting infrastructure together? So part of this is using contract tests as a way to understand the inputs going into a module are expected, as well as the outputs coming out of the module are what you expect. And ensuring that they match, right, the expected, I guess, higher level dependency on that. So there's a couple ways that you can do that, but both ways will help you decouple modules from each other and independently make changes to individual sets of infrastructure components without affecting the other. Instead, you're passing configuration between the two.
Cool, thank you much. It's time to wrap up the Q&A. So this conclude our comments, the whole series of System at Scale 2022 series. Thank you for all the speakers for the great presentations, and thank you for all the audience to participate. Before everyone go, I just want to let you know all the videos about presentations and the Q&A are available online in the at Scale web event and the Facebook page. Well, we're going to looking forward to seeing you in the next at Scale event. Which is reliability at Scale. We're going to send out the notification for register and the agenda pretty soon. Thank you very much. Goodbye.